Throughout history, people have viewed the moon as an important part of their culture. They've interpreted the moon as a god, a planet, a timekeeper, a calendar, and many other things that are significant to their culture. Ancient Egyptians viewed the moon as a symbol of rejuvenation, while in ancient Chinese culture, the moon is viewed, among other things, as a symbol of fertility and freshness in the soil. However, in modern times, all spacefaring nations have come to view the moon as a testing ground for spacecraft and space-related technologies. Since the early days of space travel, the basic technologies that we use to get into space has remained the same. A chemical rocket that reacts with fuel and oxidizer, then expels the hot gas generated at very high speed. However, the technology that we use to get out of space and land on a celestial body has changed over the years. The more we expand our landing technologies, the more we expand the type of celestial bodies we can land on, and also the amount of payload we can transport to the landing site. We're now able to land on planets, moons, asteroids, and comets. But in the beginning, the moon was our only available option in the celestial sphere. When designing a landing system for a celestial body, the main factor that determines the design is the presence or absence of an atmosphere. However, other factors must be considered: how much mass is being delivered to the surface, the distance to the body, and how loose the surface is. Of course, above all of this, the design has to consider if it's landing humans or just scientific payload. And above all of that, the design has to consider the budget available. In the early days of space exploration, the budget wasn't really a factor, and not enough data was available to start designing spacecraft for humans. The major factor was the distance. The longer the distance, the more energy is required if we want to reach the destination in a reasonable time. This means that more mass must be dedicated to fuel, which in turn will reduce the mass of the payload and ultimately the mass and complexity of the landing system. Of all of the celestial bodies, the moon is not only the closest to Earth, but is also the only one that is at a near constant distance from Earth at all times. This is very important because it allows us to go to the moon more often, giving us more opportunity to collect detailed data about the landing site and evaluate the performance of the landing system. The goal of every landing system is to reduce the kinetic energy of the spacecraft to as close to zero as possible just before it hits the surface. In addition, there must be an upper limit to how quickly the kinetic energy is dissipated. If the energy is dissipated too fast, it could impact catastrophic damage to the spacecraft or crew. There's also a lower limit for energy dissipation. This lower limit has an effect on how much time the landing system needs to safely land the spacecraft. Since a spacecraft goes through minimal change of mass when the landing sequence starts, reduction in kinetic energy will result in a reduction in velocity. But losing kinetic energy is not that simple. Newton's first law of motion states that an object remains at rest or in uniform motion in a straight line unless it's acted upon by an unbalanced outside force. On Earth, we're surrounded by a relatively thick atmosphere near the surface, so there's always the force of friction from the air or the ground that's taking our kinetic energy away all the time. Now, on other celestial bodies, the situation could be different. Ground friction is irrelevant since we're not on the surface yet. What matters the most is the density of the atmosphere. Every large enough celestial body will have an atmosphere. This includes every planet in our solar system and even natural satellites around other planets, including our moon. Some asteroids also have them. However, To be more technical, many of these smaller bodies don't have an actual atmosphere, but instead have only an exosphere. Atmosphere and exosphere are both made of gas molecules, but unlike an atmosphere, which starts from the surface of the body and extends to some height, an exosphere exists only at a certain height from the surface of the body. It exists as a ring around the body. The density of an exosphere is so thin that the gas molecules almost never collide with each other. The gas molecules are captured from space and become gravity bound to that body. In a similar way, the charged particles become trapped in the magnetic field of a planet. Earth has both atmosphere and exosphere, so do all planets with an atmosphere. When it comes to absorbing kinetic energy from a spacecraft, the exosphere is practically useless because of its extremely low density. Transferring kinetic energy to an external mass is a very effective way to lose that energy, much faster than losing it through radiation. Remember, E=mc². So, when the first attempts were made to soft land a spacecraft on the surface of the moon, the exosphere of the moon could not be relied on. The only choice was to eject mass at a relatively high speed against the spacecraft, and in that process, the ejected mass will absorb the kinetic energy of the spacecraft and take it away, thereby reducing its velocity. This is a retrorocket, looking at it from the point of view of how the kinetic energy is removed from the spacecraft. Basically, a retrorocket is just a regular rocket with its nozzle pointed in the direction of motion. In 1966, Lunar 9 from the USSR made the first soft landing on a celestial body. The landing system was based on the concept of a retrorocket. The rocket that was used was for general purpose, so it was also used for mid-course correction. An hour before hitting the surface of the moon and at an altitude of 8,300 kilometers, Lunar 9 aligned itself in such a way that the rocket engine was now facing the moon, thus making it function as a retrorocket. As a retrorocket gets closer to the surface, it's going to start blasting the high-speed exhaust onto the surface. Unless it's a large, anchored solid surface like a landing pad, anything loose on the surface will be blown around. Over the billions of years of their existence, the moon and other rocky celestial bodies have accumulated a large amount of dust from asteroid and meteoroid impact on the surface. This dust, when blown up by the retrorocket, can damage sensitive scientific instruments on the spacecraft or even damage the spacecraft itself. The more powerful the rocket engine exhaust, the more damage can be done to the spacecraft. So any landing system that depends on a retrorocket has to find some way to minimize the potential damage that this blasted dust can do to the spacecraft. There are two ways to achieve this. One is to use a smaller rocket. The other is to prevent the rocket exhaust from getting too close to the surface. Using a smaller rocket has the effect of slowing down the spacecraft at a slower rate. This, in turn, will increase the time and distance to get to the velocity needed to safely land. A smaller rocket also reduces the mass of the payload that can be carried to the surface. Preventing the rocket exhaust from getting too close to the ground means that a way must be found to get the payload from the rocket onto the surface from this minimum height. Of course, the bottom of the spacecraft needs to have some form of solid shield to protect against these debris, but the mass of the shield needs to be kept to a minimum to keep the mass of the entire spacecraft as low as possible. Lunar 9 employed both methods in the landing system. First, in addition to the main rocket that's used as a retrorocket, Lunar 9 also had 4 smaller rockets around it, pointing in the same direction as the main rocket. At 75 kilometers above the surface, the retrorocket was turned on along with the 4 smaller rockets. At 150 meters from the surface, the retrorocket was turned off, leaving only the smaller rockets to slow down the spacecraft. This step allowed a more precise control of the descent velocity, but also reduced the amount of dust produced on the surface. At about 5 meters from the surface, the payload was ejected from the descending spacecraft. Earlier, at 75 kilometers just before the main rocket was fired, the payload, which was wrapped inside a bag, was inflated. Now, when the payload was ejected at 5 meters above the surface, it dropped down and hit the surface at only 20 kilometers per hour, or 5.5 meters per second. The airbag cushioned the final impact on the surface and made the spacecraft bounce and roll a few times before coming to a stop. 4 minutes later, Lunar 9 unfolded and started broadcasting as expected. 7 hours later, mostly spent waiting for the sun to rise high enough to get a usable image, Lunar 9 sent to Earth the very first picture taken from the surface of another celestial body. When Lunar 9 started its descent to the lunar surface, it was moving at about 9,360 kilometers per hour. This speed was selected based on the distance to the moon, the gravity of the moon, how much fuel is available, and how much time it should take to get to the moon. Because of the way these parameters are related, the landing process for Mars has to begin at a much higher velocity, about 20,000 kilometers per hour. This means we'll need to dissipate more energy for a given mass to be able to safely land on the surface. But fortunately for us, Mars has an atmosphere that we can transfer our kinetic energy to, at least some of it. The bigger the surface area that's facing the direction of motion, the faster we can transfer our kinetic energy to the atmosphere, the faster we can reduce our velocity. So we can attach something like a windshield in front of our spacecraft to increase the surface, but also protect the spacecraft from the high-speed airflow. This windshield obviously doesn't need to be transparent. However, as the surface area becomes bigger, the greater the chances are for the spacecraft breaking up as it goes through the atmosphere. There's also a limit to how wide the shield can be due to the maximum payload width of the launch vehicle. So there's a practical limit to how fast we can slow down without destroying the spacecraft. Since we can't slow down fast enough while going through the atmosphere, we need to have to deal with another problem. As the spacecraft goes through the atmosphere, which I'll simply call air from now on, it will collide with and push the air molecules in front of it. These air molecules, when pushed, can only move as fast as the speed of sound. In fact, speed of sound is defined by how fast these molecules can move. Since we're traveling through the air at 20,000 kilometers per hour, that's at least 23 times faster than the speed of sound. At such a speed, air molecules hitting the spacecraft get stuck because they can't move any faster than the speed of sound, which is much, much lower. As a result of this, the air molecules pile up in front of the spacecraft. In essence, the air in front of the spacecraft is compressed. And whenever a gas is compressed, its temperature will increase. At the speed that our spacecraft is moving through the air, this increase in temperature is a lot, about 1300 Celsius at peak heating. This amount of heat will destroy any spacecraft. Since our windshield is in front of our spacecraft facing the incoming high-speed air, that's where the compression and heating will be. So to prevent our windshield from being destroyed or transmitting the heat to our spacecraft, we must convert our windshield into a heat shield capable of withstanding these high temperatures. The heat shield must also isolate the spacecraft from this high temperature. At this point, the entire spacecraft must be placed inside a capsule to protect it from the hot air that will surround it. However, the hottest air by far will be the air that's being compressed in front of the heat shield. The kinetic energy of the spacecraft is partially converted to heat as a consequence of compressing the air in front of it. The air heats the heat shield. Even though the temperature is raised up to 1300 Celsius, if the heat shield didn't have a way of removing this heat, its temperature would be rising, putting the payload behind it in danger. There are two basic ways that a heat shield can remove heat. One is through ablation, and the other is through absorption and radiation. Ablation is the process of constantly removing pieces of an object over time. In this case of the heat shield, it's the vaporization of pieces of the heat shield itself. By slowly vaporizing the outer layer of the heat shield, some of the heat is taken away by the gas generated. In addition, as the gas is produced, it pushes away the relatively hot compressed air formed by the motion of the spacecraft, preventing it from making contact with the heat shield and enhancing the effectiveness of the heat shield. In an absorption and radiation or thermal soak heat shield, as it's also called, the heat shield is designed to absorb but quickly radiate large amounts of heat and prevent the heat shield from transmitting the heat to the spacecraft behind it. Unlike an ablative heat shield, these thermal soaked heat shields are not consumed during entry or re-entry into an atmosphere. Using the surface provided by the heat shield can only slow us down to a point, since air resistance is dependent on speed. The slower our landing capsule becomes, the less effective the air becomes at slowing us down. Eventually, a balance is reached, and the air cannot slow us down any further. This speed is called terminal velocity. Unfortunately, due to the design choices we had to make to get our spacecraft from Earth and through aerodynamic heating in the Martian atmosphere, our terminal velocity is 1,500 kilometers per hour. Not exactly a safe landing speed, but it's a lot slower than our initial 20,000 kilometers per hour. The atmosphere, however, is not totally useless yet. To reduce our terminal velocity even further, we have to increase the surface area that faces our direction of motion. For that, a parachute is employed. The parachute increases the surface area from 6 square meters, that's the area of the heat shield with a diameter of 2.8 meters, to 177 square meters, 50 meters in diameter. That's the size of the parachute. Once the parachute is deployed, it reduces our terminal velocity to 270 kilometers per hour. At this point, we haven't used any energy to slow us down. We've totally relied on the atmosphere of Mars. But now, with a terminal velocity of 270 kilometers per hour, this is still far from a safe velocity for landing, and the atmosphere at this time is useless in helping us slow down further. At a height of 145 meters, we now use our retro rockets to slow us down to a safe landing speed of 0 meters per second, but at a height of 20 to 15 meters above the ground. We release the payload from the capsule and let it fall to the ground. The payload is wrapped in an airbag which was inflated a few seconds before the retro rockets fired. The airbag cushioned the impact when the payload falls from the 12 to 15 meters height. After the airbag bounces a few times, it comes to a rest. The bags are deflated and then unfold to expose the spacecraft, just like the final landing phase of Luna 9 in 1966. This landing system that was just described was used on the Mars Pathfinder, Mars Exploration Rover A, and Mars Exploration Rover B missions, but it's not necessarily required for landing on a celestial body with an atmosphere. NASA only used this method because it's a low-cost alternative to using a precision landing system that uses a parachute retro rocket system where the retro rocket takes the payload all the way to the ground. Such a system requires a rocket system that can be throttled and cut off on command. It also requires measuring the distance to the ground accurately. The landing system used on the Mars exploration rovers lacked both of these capabilities. Once the retro rockets were fired, they couldn't be turned off. Because of the uncertainty of the burn time of this kind of retro rocket, solid fuel rocket motor, there has to be a margin in when the payload is dropped to the ground. This then necessitates an airbag to cushion the landing because the height of the margin. The airbag has its limits. The more massive the payload is, the higher the risk of the airbag rupturing on impact. The landing system of a rover is more challenging to design than a stationary platform. That's because with a rover, the landing system is totally useless after landing and must be separated from the rover. NASA has developed an efficient landing system to deliver heavier rovers to the surface of Mars. There will be a separate video for that soon. No matter what landing system we use to land on a rocket's celestial body, atmosphere or not, our spacecraft will always need something to transfer its kinetic energy to, and it will always need to deal with the dust lifted during landing. It's literally the least we can do for our spacecraft. I'm Dex DFX for the Celestial Sphere.